Hello everyone, welcome to the session. I am Seshi Vidya, working as Associate Professor in the Department of ACE at R.M.K College of Engineering and Technology. So today we are going to discuss 5th unit TLRF, Transmission Lines and RF System. So in that we are going to discuss the stability considerations. So in your last session we have discussed about what is RF and microwave signals, what are the properties, advantages and applications of microwave signal, and we also discussed what is the necessity for that microwave. So in today's session we are going to discuss about stability considerations. Let us start with the amplifier circuit. So this is, for example, a single stage amplifier circuit will be considering. So here there will be an input matching network and output matching network. In between there will be a microwave transistor. Okay. So here the Z0 is nothing but characteristics impedance. So we'll be denoting that reflection coefficient. Here we'll be denoting it as tau s, which is nothing but reflection coefficient due to the source. And here it is reflection coefficient, that is input reflection coefficient towards the microwave transistor. And tau out is nothing but this is the reflection coefficient at the output side, that is output of the microwave transistor. And tau L is nothing but it is the reflection coefficient at the load. So we are going to discuss in terms of reflection coefficient at the source side as well as load side, and in between there will be a microwave transistor. So what will be the reflection coefficient at the input and output of microwave transistor? So by considering all this reflection coefficient of this amplifier circuit, so we will be discussing about stability considerations. So here what is the phenomena used in this is, and here there is an oscillation that can be understood in the context of voltage wave as we already discussed along the transmission line. So here we will be considering two conditions here. One is if tau naught is greater than 1, then what will happen is then the return voltage increases in magnitude, which is nothing but positive feedback. So which causes the instability. And the other condition is that if tau naught is less than 1, as we discussed, tau is nothing but reflection coefficient, and that not represent, it's an output. So tau naught is less than 1, that will causes the diminished return voltage, that is voltage wave, which is nothing but negative feedback. So only based upon this reflection coefficient, whether it is greater than 1 or less than 1, we are going to look at the what is stability considerations, whether it is stable one. So what is the requirement? What is the stability requirement for this? So if you consider any amplifier circuit, and first we will be considering in terms of two-port network. So if you want to analyze that any two-port network in terms of S parameters, so we will be considering that external terminations are described by tau L and tau S. So by means of tau L and tau S, we can just terminate the external output ends. So then the stability that implies the magnitudes of reflection coefficient are less than unity. That is, we can say that tau L is less than 1 and tau S is also less than 1. So that is nothing but stability. So here we will be writing that equation in terms of S parameters. So already we discussed what is S parameter and why we go for the S parameter, particularly for the microwave signals. And this tau in and tau out, which gives the reflection coefficient at the input and output side. Since the S parameters are fixed for a particular frequency, the only factors that have parametric effect on the stability are tau L and tau S. Discuss in terms of these two factors. So there are two types of stability. One is unconditional stability, the other one is conditional stability, which is again based upon the tau S and tau L values. So by considering a passive, that is a passive source, or we can consider as a load impedance, where we can just consider tau S is less than 1 as well as tau L is also less than 1. So two types of stability conditions that can be defined as, first one is unconditional stability, that is a network, any network that can be said to be unconditionally stable if and only if tau in is less than 1 as well as tau out is less than 1. For all the values of tau s less than 1 and tau L less than 1. So this is the condition for unconditional stability. For any network, any two-port network, we can say that that particular network is unconditionally stable, provided if and only if tau n is less than 1 and tau out is also less than 1 for all the values of tau s and tau L less than 1. Next one is conditional stability. So here we can say that any network that can be called as conditionally stable, or we can call it as potentially stable, that is unstable. So that is called as, that is the condition is that tau n is less than 1 and tau out is less than 1. That is just opposite to that of this condition. And only for a limited range of values of passive source and load impedances, that is tau s and tau l, but not for all the values. But in the case of first one, that unconditional stability is for all the values of tau s and tau l. But in the case of second case, it is only for the limited range. So that is a difference. So next comes about graphical solution for stability criteria. So you will be considering two types of stability circles here. One is input stability circle, the other one is output stability circle. So you will be considering both input stability circle and output stability circle in the Smith chart. So based upon that circle, we can just say that whether the system is stable or unstable. At the same time, it is conditionally stable or unconditionally stable. So we can just consider that one. So for example, for passive matching networks, say these two values in the that is inside that Smith chart, if both tau s is less than or equal to 1 and tau l is less than or equal to 1. Okay. So for the intersection of these two stability circles with the standard Smith chart, which will provide us a stable and unstable regions. So only based upon these two values, we can say that whether the region is stable or unstable. So this is the general equation, and that can be used in the circle, and for the tau plane, that is tau minus c, that is equal to r, where tau is nothing but reflection coefficient and c is nothing but center and r is nothing but radius of the circle. So by using this general equation, we can able to find out the values. So next one is output stability circle. So first we will be considering output stability circle. We know that for output stability circle, we know that tau n should be is equal to 1. So we will be writing this equation in terms of S parameter. Just by rearranging this equation, we can able to find the value of tau L. That is tau L in terms of S parameters. And we can just find out the tau L minus CL is equal to RL from the general solution. And from this we can able to find out the what is the center as well as what is the radius of that particular region. To see that, so in the first region is nothing but stable region, as I told you. Why? Because it is characterized by the tau out is less than 1 for input stability circle in the tau s plane, or we can call it as tau n is less than 1 for the output stability circle in the tau l plane. The second region is nothing but unstable. Why? Because this tau l, okay, so that it is called as output stability circle. So like able to classify these two circles. So first one is case 1, output stability circles denoting stable and unstable regions. So as we discussed, these are all the two conditions. For S11 is less than 1, the origin is a part of stable region. Here shaded region is nothing but stable. This diagram, in the shaded region is nothing but stable, and unshaded that is the region is nothing but unstable one. Okay, so for the condition if S11 is less than 1, and here it is just opposite. When the S11 is greater than that of 1, then we can say that this is the only that stable region, the remaining and all is nothing but unstable regions. So this diagram which represents output stability circles and with the stable and unstable regions. So next one is second case, input stability circles which denotes both stable and unstable. So here the circles are just opposite. In the case of first one, that is when S22 is less than 1. Since we are just considering that input stability circles, we have to consider in terms of the S parameter S22. When this S22 is less than 1, then we can say that the shaded region is nothing but stable one, the unshaded region is nothing but and that is unstable. And here it is just opposite. Only this shaded shape is here, the region is here, so that is nothing but stable. The remaining region is nothing but unstable one. Okay, so this is the input stability circles with stable and unstable regions. So likewise, by using that Smith chart, we can able to find out whether it is stable or unstable regions. And this figure represents these are all the different input stability regions. For S22 is less than 1 and depends upon the this R in value, that is the radius as well as center of the circle. Okay. And the special case is nothing but unconditional stability. Okay, so far we discussed this two types of stability. One is conditional, the other one is unconditional stability. Here there is a special case of unconditional stability is there. That's nothing but when C in minus R in is greater than 1 or C out minus R out is greater than 1. In other words, we can say that the stability circles have to reside completely outside the tau s is equal to 1 or tau l is equal to 1 circles. So that case we can call it as unconditional stability. It's a special case. So in this, by substituting that equations, we can able to find out that is a Rowlatt factor, which is also called as K. And with that, we can just find out that what is that auxiliary condition, and by using that auxiliary condition, we can able to find out the tau. So this is about the tau out, the first circle, that is the first diagram which represents tau out is equal to 1, tau out is equal to 1, so which means circle must reside outside. Okay, so this is the unconditional stability in the case of tau s and tau out planes for S11 is less than that of 1. The second diagram which represents this tau s is equal to 1, so therefore the circle must reside inside. So likewise we can able to find out the special case of unconditional stability also. So patient listening, thank you one and all.